All right, ladies and gentlemen, let's do another problem here. This also involves ideal gas behavior and the property relationships. We have nitrogen N2 in a piston cylinder device. So let's call this state 1. Got the nitrogen in a piston cylinder device, and the piston is free to move up and down. The initial volume, pressure, and temperature is specified, 1/2 cubic meter. 400 kPa and 27 degrees C. There are 5 resistors in this piston cylinder device. You can see the resistors right here. There are 5 of them. There is a voltage across each resistor and a current flowing through each resistor. The current is 2 amps. The voltage is 120 volts. There are 5 resistors. Now, the current is going to switch on for 30 seconds going through the resistors. 30 seconds, the current will switch on. I'm sorry, 60 seconds. 60 seconds, so 1 minute. And we're going to proceed to heat up the gas. And we're going to heat up the gas isobarically. So the pressure is going to be held constant in the piston cylinder device. We're going to turn on the current for 60 seconds. Presumably the gas is going to heat up. Presumably the gas is going to heat up. Now, during this heating process with the electric wires, 2.8 kilojoules of heat is lost from the gas. So the gas is getting hot, and as a result, it's radiating heat off from the gas, okay? And we lose 2.8 kilojoules out of the system. So we're heating up nitrogen in the piston cylinder device with some electric wires, some electric work, dissipating electric energy. We're losing some heat from heat transfer because the gas is getting hot. And this process is occurring isobarically from state 1 to state 2. What do I want to find? I want to find the final temperature T2. And I want to find it in 2 different ways. I want to find the approximate temperature, assuming constant specific heats, and I want to find the actual temperature, T2, using variable specific heat or property tables, okay? So I think in today's lecture, we'll get through the constant specific heat version, and then we'll finish up the variable specific heat version next time, okay? All right, so let's begin the analysis here. Clearly, this is an energy balance problem. So to find T2, I need to find like an internal energy at state 2. So I'm definitely going to have to apply the energy balance here. So let's apply the energy balance for an overall process. Q1 to 2 minus W1 to 2 is equal to delta E1 to 2. Now, I'm going to assume no changes in kinetic and potential energy. No changes in kinetic and potential energy. So delta E1 to 2 is equal to delta U1 to 2, okay? No changes in kinetic and potential energy, so total energy becomes internal energy. I have some heat transfer. What is the work? What's the work term that's going on here? Well, I've got some electric wires, so clearly I have some electric work. Clearly, I have some electric work, and I also have some boundary work going on because the system, my nitrogen, so here's my system in the dashed line, the nitrogen is expanding. It's going to expand. So I have some boundary work, and I have some electric work. So W electric and W boundary. From 1 to 2. Now let's figure out what this electric and boundary work is. W electric from 1 to 2. Well, that's going to be equal to the current times the voltage. So I times the voltage times the number of resistors times the time in which they're on. Delta T 1, 2. This guy here has units of joules per second. And of course, this guy has units of seconds. So the seconds will cancel out. Seconds will cancel out, and this guy will have units of joules. So this guy has units of joules, all right, or energy. A volt times an amp is a joule per second, or a watt. So this guy is I, voltage, N, resistors, times delta T, 1 to 2. Okay, so that's the W electric term. What about the boundary work term? That's going to be equal to the integral of PdV, expression for boundary work, from V1 to V2. Now, this is an isobaric process. Isobaric process, so pressure is constant. That means I can pull the pressure out of the integral. And I get P delta V from V1, from state 1 to state 2. Or if you like, P V1 V2 minus V1. Okay? P delta V or P V2 minus V1. So this guy here, not much room, is P delta V 1 to 2. So let's write what I got. Q 1 to 2. Now one little thing here. This electric work is on the system. It's not by the system, it's on the system. Whereas the boundary work is by the system. On the system electric work. So there's actually a negative sign in front of here. On system. That's why I got the negative work there. So I have a negative times a negative current times voltage times N resistors times delta T. And then I've got the boundary work term, which is P delta V. And that's all equal to delta U. 1 to 2. Let me take the P delta V term and put it over on the other side of the equation. And let's see what happens. Q 1 to 2, the negative times the negative gives me a positive. Current times the voltage times N resistors times delta T. That's the electric work. And then I've got delta U plus P delta V from state 1 to state 2. Now, pressure is constant. Pressure is constant, so I can actually pull the pressure into the delta V because it's constant. Okay? And so I get delta U 1 to 2 plus delta pressure times volume 1 to 2. Both terms on the right are over the process 1 to 2. So I can rewrite this as delta U plus PV, 1 to 2. U plus PV, hopefully this rings some bells here. We haven't dealt much with it. U plus PV is enthalpy. So this guy is H. So we get delta H from 1 to 2. All right? Or if you like, I'm going to put this up here in just a second. This is a long equation. I'm going to take the mass out for the nitrogen and write this as delta specific enthalpy from state 1 to state 2, lowercase h. Okay, let me rewrite this equation. A lot of stuff going on here, and I'm going to put it right up here in the corner. Q1 to 2 plus I voltage and resistors delta T equals mass of the nitrogen delta H specific enthalpy from 1 to 2. I'm going to call this equation number 1 because this is the energy balance that we're going to use to calculate temperature T2. We're going to start off with this version for both part A and part B. So I'm going to write it right up there in the corner. Let's calculate T2 assuming constant specific heat. T2 constant CP and CV evaluated at 300 degrees Kelvin. Let's assume constant specific heat. Let's recall the property relationship for, so we have dH for enthalpy. dH is equal to CP dt. Or integrating both sides, delta H is equal to the integral of Cp dt. And this is true for a gas. And if we assume constant specific heat, we get approximately equal to Cp evaluated at some temperature. We're going to evaluate it at 300 degrees Kelvin, delta T. And this is going to be delta H and delta T from state 1 to state 2. Okay? Q 1 to 2 plus I times voltage times N, forget resistors, times delta T is equal to M N2 delta H from 1 to 2, or approximately equal to the mass of the nitrogen, Cp evaluated at 300 degrees Kelvin, delta T 1 to 2. And the delta T 1 to 2 is T2 minus T1. Okay, that's my delta T. Okay, let's solve for T2. T2 is equal to the heat transfer plus the current times the voltage times delta T, and then I have N, number of resistors, divided by M Cp plus T1. So there's my expression for T2, assuming constant specific heats. I can actually solve for T2 explicitly if I assume constant specific heats. Let's see what we got. Well, I got the original temperature. 27 degrees C. I have the heat transfer. I have the current. I have the voltage. I have the time, 60 seconds or 1 minute, and I have the number of resistors. There are 5 of them. I don't have the mass of the nitrogen, and I don't have the specific heat at 300 degrees Kelvin. Let's calculate those things. CP for N2 evaluated at 300 degrees Kelvin. This is for N2, nitrogen. This is for nitrogen. Let's go to our property, our specific heat. Ideal gas, specific heats, various gases. Air, nitrogen. 300 degrees, nitrogen, 1.039 kilojoule per kilogram degree in Kelvin. 1.039. 1.039 kilojoule per kilogram degree in Kelvin. Okay, so that's from table, what is that? B10. B10. Table B10. Now, what about the mass? So that's the specific heat. What about the mass? Well, I can use IGB, ideal gas behavior. I have the initial temperature, pressure, and volume. Oops. I have the initial temperature, pressure, and volume, and I can get the gas constant for nitrogen. It's the universal gas constant divided by the molecular weight for nitrogen. Molecular weight for nitrogen is in table B1. Nitrogen, molecular weight is 28.01. Okay, so I got the molecular weight. So I can use the ideal gas law to calculate the mass in the tank. Turns out that it's 2.245 kilograms. M of the nitrogen is 2.245 kilograms. So now I got the mass. Okay, let's see if I can crank out temperature T2. Well, the heat transfer, all right, so the heat transfer, 2.8 kilojoules out of the system. So I got to put a negative sign. Negative 2.8 kilojoules. So this is out. And then I have the current, which is 2 amps, times the voltage, which is 120 volts, times the time, which is 60 seconds, times 5. There are 5 resistors. And then I have MCP. So I have 2.245 kilograms, and CP is 1.039 kilojoule per kilogram degree in Kelvin. Now, one little thing here. This term, the heat transfer term, has units of kilojoules. The specific heat has units of kilojoules in the unit. This term here, an amp times a volt, gives you a joule per second. Not a kilojoule, a joule per second. So I need to convert this term out of joules into kilojoules. So there's 1 kilojoule per 1,000 joules. And so that'll cancel out with the current, the voltage, and the seconds here, okay? And then, oh, I'm running out of room. T1 is 27 degrees C. Or if you like, 300 degrees Kelvin. I guess I'll do the whole problem in Kelvin, okay? Excuse me, get my hiccups. 300 degrees Kelvin. Running out of space. All right, let's see, what do we get? Let me crank this out for you. $329.7 degrees Kelvin. 329.7 degrees Kelvin. So T2, and this is for constant Cp, is equal to 329.7 degrees Kelvin. Okay? That's constant specific heats. Now, next time we'll do part B, which involves using the property tables, the ideal gas property tables, and we're going to calculate the exact temperature. This is an estimate, assuming constant specific heats evaluated at 300 degrees Kelvin. So about 330 degrees. We're going to get the actual temperature T2 using IGB tables, just to show you where that's going. Just to show you where that's going. Remember we had IGB air tables. What was that? B9 or something? B11, ideal gas properties for air. We don't have air, we have nitrogen. Let's keep going and see if we can find some additional tables. Ooh, ideal gas properties, selected gases. Temperature, enthalpy, specific internal energy for CO2, carbon monoxide, water, vapor, O2, and nitrogen. H and U for nitrogen. Now, one little thing here, just to show you there's a slight complication. The units on these enthalpies and internal energies are kilojoule per kilomole. Kilojoule per kilomole, hence the H bar and the U bar. Kilojoule per kilomole, not kilojoule per kilogram. So we need to use a molecular weight to convert from kilojoule per kilomole into kilojoule per kilogram. That's the only complication for when we do part B in this particular problem. We'll finish this up next time. And have a good day.